Yeah, so it is 2 o'clock, so I will make a start and start talking through this. So, yeah, so for those of you that I haven't met, my name is James McNally. I'm a LabVIEW architect, an embedded developer, and LabVIEW champion at Smith Technology, where I develop high-performing measurement systems for customers, that mostly in the scientific or the industrial space. Basically, right now seems to often involve some kind of spectral or image measurements, which is why I got interested in this particular topic. So yeah, so memory performance has become interesting to me, especially on a couple of projects. One in particular where we had to process a lot of images at very high speed. It was simple processing, but I've spent my whole life with LabVIEW, and for that we had to end up using C to get the performance that we need. And as part of that process, like, LabVIEW is very far removed in terms of a model as to how the actual processor works. And when you get into C or Rust, which is what I prefer nowadays, you're a lot closer to how the hardware works. And as part of that process, I learned an awful lot about that. Well, not an awful lot, I'm by a long way from an expert on these things, but enough to make some difference to what I was doing. And I kind of looked at this and thought, well, how does this apply to LabVIEW? And so this presentation is a bit of a summary of a few different things that I've explored with how this works. It's pretty technical in places. Please ask questions as we go, and I will do my, as I say, best to multitask and keep an eye on that. I'm going to be jumping between some demos and some diagrams. Yeah, I think the screen setup's going to make that easy enough. If it isn't, then I might jump around the slides a little bit and do more demos as we go. But yeah, please do ask questions as we go, and we'll see what we can all learn, which I'm sure will be something. So yeah, so why do we need to think about memory performance? Well, the shock is the wrong word, but it was quite interesting in this image-based application where I suddenly discovered actually we are asking more performance from the RAM than we can get, which was kind of never a concept I had in my head. You know, a lot of the time in my head, you know, RAM bandwidth was effectively infinite. But once you are working with large data structures, that isn't the case. And what we've seen over time is as processors have got faster and RAM has not moved at the same pace. So considering this kind of performance difference between them can be quite important. And so depending on the algorithm, you know, we always talk about performance and we talk about memory usage and we talk about CPU performance. But certain algorithms where you have large data structures but quite simple processing, should we say, can actually be hugely influenced by the memory access patterns that you use. So to start off, I want to talk a little bit about the hardware that is sat in your computer that you're on right now, probably. Somewhat like this on a phone. But the diagram here shows a slightly simplified view of the memory architecture from a modern Intel CPU. The numbers are based on what's in my laptop, which I forget now, it's a 10th generation i7. And I've simplified it just to 2 CPUs because that's all we really need to make the point that we need to make. So, you know, if you drew a block diagram out of a computer for someone, quite often you might just have the CPU connected directly to the RAM. But actually, one of the ways that computers have managed to increase the CPU performance despite memory not improving at the same rate is increasing levels of memory cache between the CPU and the RAM. So your modern, as I say, Intel processor has 3 levels of cache. And the basic idea is you have fast, very local cache to the processor up to a slower but larger cache close to the RAM. So what we see now is per core on an Intel computer, there is a level 1 cache, which is very small, very fast. On my system is about 80 kilobytes per core. And that's actually split between caching instructions in from memory, and caching data in from memory. So for an actual data structure, it's probably more like 40 kilobytes. Of course, if you have hyperthreading turned on, half it again, or there's some different modes it can use, but it gets shared more over. So yeah, I mean, there's not many computer specs that still come in kilobytes. This is very small, but it's very fast indeed. Then we have a level 2 cache. So this is probably, when I've been working on performance with this, this is probably the one I've got most in my head, because I've probably got something that's big enough that isn't going to fit in the level 1 cache. But what I really want to do is keep it close to the CPU. So it's about looking at this level 2 cache. So here we get into a megabyte, maybe a bit less, maybe a bit more, depending on the age of your processor. This is per core still on current Intel processors. I think if you go back maybe 10 years, this used to be shared between a pair of cores. So if you had a quad core processor, 2 cores would have one cache and 2 cores would have another cache. But nowadays they have a single level 2 cache per CPU. And working out, again, we have the level 3 cache. So this is shared between all of the cores. So this is much slower. If you've ever seen a picture of a CPU die, this is normally a big sort of generic block in the middle. So it's further from where the actual processor is performing the computation. But we can get much bigger. It's much cheaper and easier to put on a die. So in my case, there's 24 megabytes of this. So you're getting into tens of megabytes then for that cache. And obviously the RAM itself, where you're going to be in the kind of gigabyte range. So what that actually looks like in terms of performance is tricky to nail down. It varies per processor family, processor architecture. It's actually generally measured in processor cycles, so it's varies depending on the clock speed that your processor is running at. So I found these tables for an Ice Lake CPU, which I think was the 10th generation Intel CPUs. And I've just assumed 4 gigahertz as a, if you're on power and reasonably well clocked. Actually, I was going to do it at 3.9, then realized 4 would be a much simpler number to work with. So the level 1 cache has about 5 cycles of latency. So from being requested by the processor to load something back. So that's about 1.25 nanoseconds. So, really low nanoseconds here. And actually, I should say, by the way, with all of these numbers through this, the thing to kind of take away is an order of magnitude as opposed to necessarily the actual numbers, just to get a good feel for, being able to do kind of back of the envelope calculations is really useful, which I'll show later. So the level 2 cache is, 2 or 3 times slower, about 6 nanoseconds in this case. The level 3 is now getting us out to about 10 nanoseconds. And then there's a big hit when we go to RAM. So in this case, it measures out to about 97 nanoseconds, 100 nanoseconds. I've seen various rules of thumb that say more like 50 nanoseconds or 70 nanoseconds. But I guess the point is, again, as an order of magnitude, it's talking high tens of nanoseconds for a RAM access. And getting a feel for these numbers means we can look at certain algorithms, and I'll demonstrate this later, and we can start to kind of look at the performance we're actually seeing and understanding whether it seems correct or not. I see the question, Imran, about RT. Yeah, I will try and call some of this out. You know, to be honest, I'm not sure it was yourself. Someone asked me about this in advance of the presentation as well, and you know, it's really none of it is very different, if at all. You know, the current generation of systems that NI have for LabVIEW real time are all x86. I mean, there's some older ARMs. That might be the main difference if there's an ARM processor, but most of this is actually tied to the hardware architecture rather than the operating system. So let's see. Let's do a first little test demo. So as with everybody, I have VMs for LabVIEW development, and luckily everything still seems to work quite nicely. So let me just load the right project. So the first thing I want to do is kind of demonstrate some of these numbers. I'll ask out and back. Yeah, Christian, so how do the various cache levels interact, and how does data move from one to the next? So the important thing to understand, as I've got from this, and I forget there's a proper term for it, is if data is in a higher level, if data is in the level 1 cache, it is also in the level 2 cache and the level 3 cache. So they kind of, there was a proper phrase for it, which I've forgotten. They stack up on top of each other. So the, and my understanding is it isn't kind of a, it doesn't cascade, I don't think, based on the numbers I've seen. So you don't pay for a level, well, no, sorry, yes. The numbers I've shown there, sorry, I think are, you know, you don't sum them up to get to the final number. So the 100 nanoseconds for RAM means you've missed level L1, L2, L3, and then you've gone to RAM. You don't take that 100 nanoseconds and then add the delays for the other levels as well, is my understanding. Hopefully that's the kind of thing you're interested in. So what I've got here, so this is running in a VM, but again, this is all really about the hardware architecture. So the effects should work the same way in the VM as they do in reality. So this is a quick piece of benchmarking code I've written. I forgot I put the time structure on there. I'll explain that one. So what we're doing really is creating an array of a fixed size. In this case, a 2D array, but that doesn't actually really matter. And then I'm benchmarking the time to read an element out of that array and put it in an output array. So that's what we're actually benchmarking here, is kind of that read and the build here. And the reason I do that is just to make sure that LabVIEW doesn't simplify this code to nothing, because we're looking at very small elements. Actually, I just seen there's a couple more questions coming up. I'll do the demo. I'll come back to those questions, but I have seen them. The time structure will be there to force this to always run on one core. So I had actually been meaning to ask the question at the time, and still haven't, of someone, if there's any risk that LabVIEW would move this between cores, because that will obviously impact the caches that we can access. So this just ensures we're sitting on one core, but the other benchmarks, you'll see I left this out. I didn't see any evidence that would actually happen. So by doing random accesses through these arrays, we should be able to see that when the array is small enough to fit in the smaller caches entirely, we're not paying any performance penalty to go out to outer caches. So if I run this, it's not like a step function, because you get a point where some of it's in cache and some of it isn't. But here we can see the rough sizes. So the size down here is in kilobytes. So this one kind of changes each time as to how much it ramps up. We can certainly see there's a period here where we've got everything in level 1 and level 2 cache. And so we've got sub 5 nanosecond times for kind of accessing that data. This step up here, probably to around about here, and I'm trying to see, 24 would be about here, but this kind of slope here is where we're going to be hitting that L3 cache. So we're seeing that kind of ramp up until we're hitting 20, 25 nanoseconds, where that would actually end about there. And then we see a big step up again as we get more and more of it in RAM. So maybe with bigger ones, we'd see it continue a little bit further, but you can see we're getting to that 80 nanosecond level. So the numbers aren't precise, but it gives you an idea that those kind of scales exist, and we can actually see that in the software that we write. Fantastic. So there's a question about, can the CPU write directly to the RAM, or does it need to go through the cache? I'm honestly not sure exactly. My kind of basic understanding of how that would work, though, is I think it would have to perform all those actions essentially in parallel, because if it writes to the cache, it needs to write to the cache, and it needs to write back to the RAM. And what happens is there is some kind of algorithm that I won't even pretend to understand, which communicates between the different cores to say, oh, core 1 has just written to this address that you've got in your cache. So that cache data is now invalid. We have to go back to RAM to next time you try and access that. So it's got to go all the way back to RAM, or at least to L3, so that it can sync up between the cores. And if two cores have the same data in their caches, it needs to be invalidated. Question there on preparing dynamic dispatching for upcoming executions in the cache. So yeah, the definition of kind of the dynamic dispatch is it's not predictable at compile time. I mean, maybe at runtime. Sorry. Dynamic dispatch is designed to be unpredictable. So the way that's going to hit you when it comes to things like this is that instruction cache. So that instruction cache is going to give us the it's going to need switching around. So if you've got 5 different dynamic dispatch methods and they're all very big, so they don't fit in that cache, you're going to see more of a penalty than if they don't. There's no real way to prepare it ahead. If it is possible to determine it at compile time, I imagine LabVIEW substitutes it out anyway, but I'm not entirely sure. I know Oleg's asking, is it really possible on a Windows system to measure processes up to nanoseconds? So yes, it's never possible to measure these things perfectly. The way that I'm kind of compensating for that is you probably saw the runtime. You know, these are running each time 1 million, 10 million, I forget how many zeros I ended up with them, 1 million accesses. So averaging over that million with the high precision timer is perfectly reasonable for kind of what we need to see. But yeah, I mean, don't put too many decimal points on that. It's not as precise. As I say, I think the really important thing with these numbers here is understanding the kind of scaling of that. And then as we go on, I'll show you some examples where these kind of things really add up into a bigger effect. Please excuse that printer. But yeah, essentially, Oleg, you just got to average a lot to make it mean something. So there's a few elements to the way that caching occurs in processors. I'm not going to go into the whole way that there's a bunch of stuff as to how it translates addresses into where it should be in the cache and things like that. I'm ignoring that for the purposes of today. I'm going to link to a book at the end, which I found really good for going into a lot of stuff like that. But a useful thing to be aware of is that the way that cache works is it divides the memory into discrete elements called cache lines. And the default right now certainly on Intel x86 processors is 64 bytes per cache line. I think, again, if you go back 10, 15 years, maybe there were a few more that were at 32 bytes. But this, as far as I can tell, is pretty standard right now. And what that means is that the size of kind of the steps you're going through memory affect how fast you're going to burn through your cache, if you like. This is an example, and I'm going to show an actual demo of this in a minute, where maybe we have a cluster that's 24 bytes per element. And what 64 bytes per cache line means is actually in one load into the cache, we're going to get 2 2/3 of an element. And we've effectively got 3 elements here in 2 lines of the cache. If we have 64 bytes per element, then that could fit perfectly into 2 cache lines. Or if it's not aligned with the memory boundaries, you might find something like this pattern at the bottom where you actually end up with 3 cache lines to load in those 2 elements. And where this becomes important is obviously it's kind of the utilization of the cache. So like in this case, if we wanted to load these 2 elements, we also have to load the equivalent memory of a 3rd element as well. And then I've got an example with 96 bytes per element. So in this case, we have to load 3 cache lines to even get 2 elements. So even though, as I show you, we're only loading part of this, we still, from the caching point of view, we have to load the whole data structure, or at least 64 bytes of that data structure at a time into the cache. So I've got another demo. This demo kind of doubles up as a couple, so I'll cover that. I'm going to do things slightly out of order here. So what this demo is going to do is it's going to show us some of those cache effects, and it's also going to show us about quite a concept that goes back, if you look back at some of the old LabVIEW performance material, about whether to use arrays of clusters or clusters of arrays. So maybe I shouldn't be using multiple purposes in one screen at a time, but hopefully it'll make sense. Does the code look as dodgy to you guys as it does on my playback of this? I'll try to point it. The resolution looks a bit bad, but I think it's just because it shrunk it for me. That's all right then. So here I've got 2 different arrangements. So let's assume that you are pulling in a bunch of channels on a data acquisition system. You have a couple of options as to how you arrange that data. You can have a series of rows where each row is a sample in time, and you have that data next to each other. So that could be done with a 2D array, or in this case, a cluster, because I wanted to control the size a little bit more. Or you could load each channel as a full array of data of each timestamp and put those into a cluster, which is what this last option does here. So that's what the difference between the clusters and the arrays is. And then what I've got here is those 3 different sizes so that we can kind of see some of the effects of the cache lines here. So we've got a 24-byte element cluster, got a 64-byte and a 96-byte. And then what I'm doing here is kind of a little bit different to the last one, but with some similarities. So I'm generating 10,000 copies of which of 3 channels we'd like to load. So these are like a channel index. And then for each of these cases, we're going to pull out that entire channel's worth of data. So imagine you wanted to take one channel and plot it on a graph out of this whole data set. So for the cluster of arrays, it just means reading out that array. For the clusters of channels, it means reading that single channel out of the cluster and building the array out of it. So when we run this, the first few here repeated, you can see I found this one just needed a bit of a warm-up sequence to get consistent. So you can ignore these kind of first set of results. So here we can see we have the clusters from largest to smallest and the cluster of arrays. And the important thing here is, well, there's 2 effects we can see. The first thing is the cluster of arrays, because we wanted to make a whole array out of it, is much faster. It's about 21 microseconds versus about 50 for the clusters. And that's because all of that data is already stored in the right format that we want to read it out of and contiguous in memory. So when we go, even though we are reading that and building a new output array from it, because it just follows in memory, it's contiguous in memory as one structure, we get the full optimization kind of pipeline of the memory, because it's going to assume, oh, if you read address 1, you're going to want address 2 next. So that'll already be fetched into cache by the time we come to read it. With the clusters, we're making bigger jumps through memory. So essentially, the 24-byte cluster, we're jumping through 24 bytes at a time to find the next copy of that channel data. The 64 bytes at a time, and 96 bytes. So in the 24-byte, in one line, we're going to get 2 or 3 levels. One cache line, we're going to get 2 or 3 elements that we actually need. In 64 bytes, we're going to get 1 per cache line. And in 96 bytes, we're actually going to have to skip over some of those lines to kind of make it work. And that's why we see these small performance variations between these. So the 24-byte is slightly faster by, what's that? Probably about maybe 10% than 96, but not as dramatic as the cluster of arrays. But as with a lot of things in computing, when you're looking at storage performance, you've got to think about how you're going to access that. If I change this and say, actually, we want to pull out a row of data instead of an entire channel of data, then we'll see that dynamic changes then. Because, again, in the cluster case, we've got all of that data packed together in memory. We have fewer cache lines to get, hopefully fewer cache misses to fetch that data. And I was going to drop the number of test cases on this one. There we go. Still not too bad. So this one, yeah, we're just pulling out a lot less data, so it's a lot faster. You can see the cluster of arrays is actually much slower. Well, not much slower. That's probably not really fair. About 20% slower than our channel clusters. I need a better term for those two types of clusters, don't I? But these are all memory effects that we're seeing in how the memory is laid out. And then hopefully you can see, because with these different clusters, we're seeing the effect of that caching as well, and how that impacts it. Now, this is one that everyone will be somewhat familiar with, because that's how the execution priority affects the results. Yeah, I mean, this is something where we can't really, we're limited to the amount of control we have, especially in LabVIEW, because it has its own scheduler and where it's going to put it. For all these benchmarks, the goal has been remove debugging, make sure they're all reentrant and things like that to try and get the maximum effect. But yeah, I'm not going to lie, that one is quite performant. Which is, how does the size of the outputs impact performance? It definitely can. Let me remember what I actually did on these, because I did have a play with this in the different formats. Yeah, so we are also benchmarking the writing of the output here. We're not actually just benchmarking what we're doing. If I had a bit more time to play, I might have played with some different formats of this. What I've generally done, when we're building a 1D array, that should be pretty consistent, because LabVIEW can pre-allocate that, and we've got a single write without any additional buffers. But it is a good, well, I'd expect it, Christian, from you, that that's the something to consider here. And yeah, I never got around to playing with how much I can remove and not lose the not have stuff optimized out. But yeah, to be frank, it's one of those cases that the numbers make sense and we're consistent enough that I'm pretty confident that it's showing something meaningful, even if, yeah, exactly as you say, the certainly in this case, if we had bigger, longer channels, then potentially that would make a difference, because we're getting different size arrays. But the writing output of the arrays should be very fast, because it's always sequential. And certainly in the 1D, I don't actually know in this case how smart LabVIEW is pre-allocating this array, which is an interesting question. But I imagine you would take a hit on the first or second iteration, and then it should be pretty consistent. So speaking of multidimensional arrays, that's a nice segue for me there, Christian. Multidimensional arrays are a lie. As far as the computer is concerned, they don't exist. We have, a block of RAM, which is just, just think it's one flat address space. And what happens, and a lot of you are probably already familiar with this, when you have a 2D or a 3D or any kind of multi-dimensional array, is that there is some kind of translation into how that array is stored in memory as kind of a flat sequence versus how it's represented in your software. The most common of this, it's not exclusive, but the majority of languages do this in what's called a row major concept, which is we store all of the first row and then all of the second row and then all of the third row. And so then when you're going in and accessing an element, indexing an element out of this, you're telling it which row, and we'll skip ahead by a row times the size of a row of memory, and then which column, and we'll skip into the column that we want. Now that is really important because it's one place where the software can look nearly identical, but you can get dramatically different performance profiles out of it. So this is a test of kind of the 2D access patterns. Very similar to what I've shown you before. In this case, we have 4 different mechanisms. We're going to build a reasonably large 2D array. What's that, 2,500 elements square. And we're going to pull out either entire rows or entire columns based on a random index so that we're moving through the full size of the array. And we've got 2 kind of base cases here. One is pull out an entire row. One is pull out an entire column. And then everyone's used this a lot, right? This transpose. I've certainly done it when you pull it out of a DAC task and you're not pulling out the elements that you want. I want to show you what happens when you transpose in LabVIEW, because it is clever and not clever at the same time. Or clever may not be as helpful as it looks. So I'm just going to run this. Again, I've got a couple at the beginning just to show kind of a bit of a warm-up. So row-wise, reading out of it row-wise is very fast, because what we're doing there, it's kind of like our same thing with our clusters and our arrays. We're pulling out one row, which is one long string in RAM, if you like. I probably shouldn't use the word string there, but one long piece of memory in RAM. So that's very fast. Again, it's going to fetch nicely into the cache, because the CPUs can say, oh, you wanted address 1, you'll probably want address 2 next, you'll probably want address 3 next, and it's going to prefetch some of that data into the cache for us. But if we want to pull out a column, we are instead jumping through the memory at whatever the width of a row is. So instead of getting contiguous elements, we're now jumping, certainly past the cache line in most cases. And so we're going to see a big drop in performance, in this case about 5 times, about 8.5 microseconds to 42 microseconds. The reason I wanted to include transpose is transpose in LabVIEW is a bit clever, where it doesn't do anything with the memory. All it's doing is creating a new kind of view into the memory, and then internally the compiler essentially knows when we ask for a row and the array has been transposed, we're actually asking for a column. So it helps if your main problem is my rows and columns aren't the way I want them to, but sometimes you might want to do a transpose to get better performance, and this isn't going to work for that. So that's very common if you've got something where you're doing matrix multiplications. You might pre-transpose one of those to make the algorithm faster, but doing it this way isn't going to cut it. I was trying to remember, I didn't actually check this before. Sometimes with these, you'll actually see it labeled as a subarray, but in this case, we don't. Yeah. But yeah, so be aware of transpose. It's a good productivity feature for the developer, but it doesn't help with performance if performance was the concern that you have. I was just thinking the same thing, Christian, and I haven't tried it. Should we try it quickly now because I'm a glutton for punishment. I will code on the fly. Let's see. Always copy. Let's have a quick look and see what that does. Although actually, because we're doing it every time, that won't be. You'd have to always copy it outside of the loop actually to prove what I was trying to prove. That won't work. There you go. That's why you don't make things up as you go. But yeah, it's a good question, Christian. As I was just talking through, I thought I should have said what the way is to do that, and that would be the obvious thing to try is do a transpose and then an always copy. I don't know if that would then copy it as a transposed element. One to test later. Oh, how are we doing for time? Yes, exactly. So the benefit is the transpose takes no time at all because it's not actually manipulating any data at all. It's kind of if the right phrase is a compiler trick or a language trick. Okay, how are we doing for time? We're looking okay. I might have to cut the last bit slightly, but we'll see how we go. So I was out at NI Connect in Munich last week presenting on Python. Gabriel's just asking a question as well, which I'll address first. Do these type of operations get improved performance on CPU with large L3 cache, or is L2 cache the most important factor? I mean, L3 cache is all going to help. Yeah, because there's another slight element to this, which is it depends on some of the CPU architecture. So depends on, there's something called, the cache has a number of ways, which kind of says how different addresses conflict with each other in the cache. Because the profile is quite a big step up in performance from L2 to L3 cache, I think making it so that these arrays would fit in the L2 cache, either by making them smaller or making the L2 cache bigger, is probably going to give you a better performance boost than a large L3 cache. But I mean, it's all going to help, and ultimately, you know, it's kind of a design trade-off thing at the hardware level as to how they kind of balance these layers out. But yeah, I mean, from what we've kind of seen and thinking of those initial kind of cache numbers, a bigger L2 cache, I think, is going to give you a larger impact than an equivalent growth in the L3 cache, probably. But I realize that that's really hedgy, but yeah, it really does depend on a lot of factors. Paul, yeah, that's it. It's always been one of those question marks in my head with the transpose. I'm like, should I be doing this or should I be going back? Now, what you could do actually, you know, said about can you force a transpose and a copy? The other thing you can do on some APIs is you can configure which way it is read out. So, for example, on the DACMX APIs or the TDMS APIs, I think you can do the same. You can tell it to read it out as interleaved, or I forget what they call the other one. Now, I haven't tested this. Decimated, yep, that's it, yeah. I haven't tested this, but I've seen this. The next time I come across that, I might be tempted to go back and try and change how it reads out of the API instead, so that it comes out in a better format rather than just dropping the transpose. But I mean, all of this is looking at very small time numbers. I mean, for most DACMX applications, it's probably not going to make a vast difference anyway. So speaking of data formats, that actually hands off quite nicely. So yeah, so I was at NI Connect doing a demo for using Python and OpenCV. I'd been asked to kind of do a presentation about using Python with LabVIEW, and I've always kind of wondered about the OpenCV path, and I think that was a common question. So I created a demo, and the biggest problem I had is the data formats that are expected. So LabVIEW and IMAC, and the idea was here, I was going to capture the image with IMAC and then pass it to OpenCV for data processing. So the way that the IMAC data comes out for a color image is we get a 2D array of 32-bit numbers which contain the red, green, blue, and alpha channels. The way that OpenCV expects the data is as a 3D array where you have the kind of third dimension is which of those channels. So in its case, actually, it wants the order blue, green, red, alpha. And they're 8-bit numbers instead of 32 then. So I realized I kind of need a bit of a backstory to this, which was I was kind of surprised when I first did this, and I kind of did the naive solution as I would think to do it. And well, actually, I didn't do that. I did about 3 different ways and kept getting numbers to convert this data between 200 and 500 milliseconds. Christian says, I see a very stale slide way forward. So it should be on one saying initial implementations were slow. Yeah. Okay, yeah, I'm afraid, Christian, looks like it might be a problem on your side. I'm not on a VI anymore. I'll give Christian a second to see. Jorgen, no, I haven't really written it up as formal as that, but I can share all the code basically if you want to have a try with these things, and I'll send over a few resources at the end as well. Yes, Christian, hopefully you can get something going. Oh, excellent. Yeah, so I was doing this with a webcam, and there was a really noticeable video lag. And as I say, the transform was taking hundreds of milliseconds, which seemed big. So my kind of initial question based on the project I did before is it because we're copying data? So in that case, I mean, we're trying to go a lot faster, but we kind of couldn't even really afford data copies. So the first question I kind of asked myself is, could we not copy the data? Could we just pass the same piece of memory straight through? I thought a copy might be costing us time. We might be able to manipulate the data in place, because multi-dimensional arrays are a lie, as I said earlier. And kind of data types are a lie. This isn't true. It's a lot more complicated than that. But really, our U32s and our U8s kind of sit on top of each other. So the actual data in memory between what LabVIEW wants and what OpenCV wants is very similar. We just have to swap a few of the bytes around. So originally I was kind of thinking, well, can I do something really clever? You know, that clever software that you can never work out how you did it afterwards to avoid these copies. And this is where I was already researching this presentation, which handily set me up with some numbers. So I went back and said, well, okay, if it's because we're copying the data, what does that look like? And I kind of attacked this problem from 2 different directions. The first one is like a real airy number of, well, if DRAM can do about 20 gigabytes per second, what would that mean? Which was a number that I'd found, frankly, Googling on the internet. This means 0.4 milliseconds per data access, or 0.8 milliseconds for a copy. Excuse me. Another way to look at it was going back to the kind of numbers I had earlier for the RAM access performance. So these were 1080p images, so they were about 8 megabytes. that means if we divide that by 64 bytes, we're looking at about 129,000 cache lines that we need to access. Using the number I mentioned I'd found earlier, about 70 nanoseconds per RAM access. This is ignoring all capabilities of prefetching and anything that might be in RAM already, etc. That would come out to about 9 milliseconds. So 1 to 10 milliseconds seemed reasonable. And at this point, I actually went and benchmarked this in Rust as well, and found sort of 1 to 5 milliseconds being typical. And so this actually made me think the issue isn't with a copy. So I didn't want to lose the copying because it's really useful. Buffer management is much easier. There's a higher risk of bugs if you're trying to do things in place. When I've worked out the numbers, actually, it seems like the performance is way off anyway. It's not just a copy. 300 milliseconds. This is 5 milliseconds. Just didn't seem right. In theory, we have time at 30 frames per second to do this with a copy as well. Obviously, depending what else is going on. And then, to be honest, I did try this anyway in LabVIEW and couldn't find a nice way to do it. So I just couldn't do it with zero copy in LabVIEW. So this was my naive solution. So we have the 2D U32 array in here. We auto-index it out, pull it out the elements, and actually I don't need the alpha. So we just pull out the 3 color elements that are needed and build it back out into a 2D array. I tried this with and without parallel. It made a small difference, but not very dramatic. I think maybe 10% difference with 4 cores, something like that. I'm curious to see. This took me a little while to kind of suss out. If there's anyone, and I'm imagining there might be a couple of people on here that may have already come across something like this and be able to guess where the problem lay. Build a new 32-bit number. Not quite. Let's see. So what I realized afterwards is, well, not afterwards, after a bit of experimentation. Yeah, I think Paul is kind of on it. So I think LabVIEW is still creating these intermediate buffers independently. So rather than having one big stretch of memory that we're writing into, it's building a 1D array, which is then copying into a 2D array, which is copying into a 3D array. I've not 100% confirmed this with people who would know, and I imagine Phoebe or Krista or someone else might be on it. Ah, good, Derek's seen this too. This is my new feeling, Derek, is auto-index outputs are a problem. So yeah, so I did this translation, create an empty buffer, and directly write it in. It's a bit of a mess still. I kind of might come around to clean this up. This dropped from 300 milliseconds to 60 milliseconds. So this is because we're not getting extra intermediate buffers, which A means extra data copies, B means when coming back to caching, we've got multiple a lot more data we're kind of manipulating during the process. So this can still be improved. I mean, this could be pre-allocated once and do things like that. But yeah, it's ultimately, I think this can be improved, but this was the big jump. This got me to about 10 frames per second, which was enough for the demo. Yes, Piotr, exactly that. Yeah, that's what I thought afterwards. But it depends on how strict you want to be. So, whether you need to say, well, actually, the input dimensions have changed, therefore I need to reallocate it to do resize it. But you could do that detection probably for the cost of creating it, because we don't need to zero it out every time because we're going to be rewriting it. So yeah, this is an example where I find LabVIEW, is great for so many things, but memory control is not one of them. 9 times out of 10, it doesn't matter. But yeah, really what I want to do is create this buffer off once and kind of manage that as we need. But yeah, exactly that. There's definitely improvements. Gabriel, yeah, reshape array. Let me see if I've got them all here. So I was trying to keep all the different versions so that I could remember what I tried. So that was the simple one. Oh, this was just trying to use a cast instead of splitting the number, which was slightly slower but very similar. This was my first attempts at kind of just working with the array shapes. But yeah, this was much, much slower because it turned out in the end, typecast made a buffer and each reshape made a new buffer as well. So we're getting multiple copies in there, which really impacted the performance. Yeah, I thought that was just a nice little example where kind of knowing some of these numbers helped decipher what was going on something that was going on. So, yeah, so in-place structures, there wasn't really an opportunity on the naive version anyway, because we had to change data type. So replace array, there's no real benefit to in place anyway. And then on the other formats, because we were also changing from U32 to U8, you couldn't really do it in place as far as LabVIEW was concerned because it's a different type. You know, if you were in C, you could just do a pointer cast or something like that, with all the problems that can entail as well. So VB, yeah, I think I didn't play enough with the Python node to understand if that was possible. I think going to C++, I could just put a U32 array in and kind of let the boundary do the cast. With the Python node, it's actually looks at the LabVIEW data type and tries to convert it into the same type as a NumPy array. So I was looking for some clever ways to do things like that, but you could do that. Typecast it in LabVIEW. Yes, a good question. I tried this, but I think if I understand what you're saying, the problem is you can't typecast a multi-dimensional array. Because as Derek alluded to, it's just like a flatten and unflatten, so it doesn't know what dimensions to use it. So this was my attempt at trying to do this all with just kind of casting. But this will only work with 1D arrays. So I think I was surprised it didn't take a 2D array. I had to reshape to 1D array, cast it as a 1D array, reshape back to a 4D array, a 3D array, sorry. Yeah, so I don't know if that's what you mean, but yeah, I thought there would be a nice way to do that. And I mean, there may still be. I didn't spend hours on this. But yeah, I couldn't feel out a nice, simple way to do that. John's asking about iMac to external DVR. Yeah, I think I didn't get that far, to be honest with you. I was trying to remember. I even feel like there was something. There's a few different kind of array manipulations in iMac, but this was the only one I could find shortly that could work. But yeah, external DVR. Actually, that would be interesting because this node takes time as well. So this is like actually doing a copy out to a LabVIEW array, and that takes a decent chunk of time as well. So that might actually allow me to cut that time out. So we're not doing the copy out of it. Christian asks, can you operate on the 1D array directly? Again, I could if I was going to C, but the Python node is smart enough to then say, pass a 1D array to OpenCV that it doesn't understand. And I tried doing that and reshaping it in Python, and it was slower than reshaping it in LabVIEW first. So yeah, I did have a play with that. I suspect there must be some efficient way to get OpenCV to just take the 32-bit array. But again, I don't know. I know, yeah, as Phoebe says, like doing OpenCV is C++ calls from LabVIEW would probably be, if you really wanted to do this now, I would say do that. Don't use the Python mode. Or just acquire the images in Python straight away so they come out in the right format. Cool, right. I am going to skip the next slides. Well, I'll quickly talk through this, but I won't show the demo because I'm running out of time. But another thing I'd have to think about with this is pipelining. So pipelining, traditionally, you're passing data from one loop to the next. If that's then running on different cores, which you would hope, then it means you're invalidating all the cache as you go through. So I think there will be cases, and I don't have a hard and fast rule for this, but there are cases where it's faster to have multiple threads taking one piece of data through every step of the processing, so that you're not removing data from the cache. Have a think about that yourself and come back. I haven't quite get a good benchmark for that anyway. But I did a rough one, and yeah, I'm not even going to try to explain this right now, but yeah, depending on the size of the data, that might be more efficient. And that's about my time up. So thank you. That's great. Thank you for asking questions as we go. I'm still happy to have any more. I can't remember if I'm supposed to be done before the next session starts or not. At what point? Probably am. But yeah, just a quick couple of resources. Obviously, I must have a way to share these slides. There's a nice plot I found of showing some of the different caching effects. The inspiration for a lot of this is a book called Understanding Software Dynamics by Richard L. Stiles, who used to do performance for Google. And yeah, it will tell you all about measurements and how dodgy some of it can be. And I still have to work through a lot of the books. It's fascinating. There's this GitHub, if you search numbers every programmer should know, there's a bunch of copies of this, which kind of have some of these rough numbers and for different things. And, you know, LabVIEW help for how LabVIEW organizes these things in memory and stuff like that is pretty useful as well. So thank you very much. I think you can, yes, so John, I was about to say, so I don't know if there's somewhere we can chat in Hopin still, or find me. I'll hop over to the Discord as well. And have that up, and yeah, I'm certainly interested in chatting some more if you've got questions. Cool. Christian says this session's good to stick around. What does that mean, Christian? So I can stay here, or we have to break out somewhere else to chat more? I don't know if someone else comes into the same room. Oh, I can stay here. Cool. No, that's all right. I'm yeah. Normally I would have done a bit more research, but I'm still a bit fuzzy traveling last week and snuck up on me a bit this morning. So was it John? John was asking about iMac and C++ and Python. Oh yeah, we can come back to that. Jorgen, so there is a Discord for LabVIEW, and there's a GLA channel someone created on there. So yeah, I'll keep an eye on that. I'm getting quite used to Discord. I quite like it. Oh, John's getting set up. Yeah, do. Yeah, so let's see if I can get it open. I was closing everything down because I was. Some of these demos operated at the edge of the memory that I had, so. Let me see if I can remember how to share one. Share a link for it. Invite people. There we go. I'll put a link in the chat for the LabVIEW Discord. Thank you, Maxime. Yeah. That's being the challenge with all of this in LabVIEW is there's not many tools to control this stuff, so it's just interesting to figure out how on earth LabVIEW is doing it, and the CPU, because as I say, a lot of this stuff, all these numbers are influenced the same whether it's LabVIEW or any other language. It's just how the hardware works, which I find quite intriguing for whatever reason. It says, yeah, I don't use iMac. Yeah, I mean well, not so dirty secret. It's quite obvious. If you didn't have to, like, I would just acquire the images directly in OpenCV as well, because then it avoids all of these translation steps. Just a striker pushing away from C and C++. Yeah, so this is where I like Rust. I'm a big fan of Rust. I'm doing more and more work in Rust where you still get an awful lot of control, but it's got a lot more guardrails on it. So you can get the same kind of performance out of Rust as C, C++, but without so many risks as just dealing with raw pointers. But yeah, and then this stuff applies across the board. I saw a write-up recently, one of these kind of coincidental things from Netflix about trying to optimize some performance. Oh, John has requested it there. Let's see what I can do. Yeah, they ended up having to play with the JVM as to how that laid out memory to improve its cache performance to get some of this. So yeah, it's going to turn up a lot. So I'm just trying to work out how this operates, John. I saw you pop up at the bottom. The interface with Rust? Yes, so Rust is quite compatible. That's the way I'd describe it, with C and C++ type interfaces. So you can compile Rust as a DLL and call that from LabVIEW. So I've done that on a project or two now. Let me stop sharing my screen, John, see if that lets me see anything more. I saw you pop up and now I can't see anymore.
Hello.
Hello.
Hi, how's it going? Thanks very much for your talk. It was yeah, really interesting. I think you covered some of it in a C-Slug, which was great, and it was nice to see a bit more stuff. So yeah, fun to see how you're getting on. Yeah, so I have been doing a bit of stuff. I talked about it at my GDev talk where I was talking about augmented reality, which I'm sort of plumbing.
Oh yeah, I remember
some OpenCV stuff into LabVIEW via C++. But then I just got really into iMac things, and I did look at passing, because you can get a pointer to iMac memory, like a memory address essentially, and then I tried passing it through to Python, but I think that the Python node runs in its own separate process. Like, it's essentially calling the Python exe, and it sort of flattens data and passes it backwards and forwards. So I guess you can't directly pass a pointer. Yeah, so I think that's that copy is what sort of killed doing various things.
Oh, that's interesting. You saw the same thing then, yeah.
Yeah, even if you try and do all the crazy NumPy stuff on the Python end, it doesn't help. Yeah, so I think that's what I've tried, and in the end I was just using C++. So I do get access to the LabVIEW memory, and it's easier, I should say.
Yeah, because I think, you're always going to have the problem with the Python node. I think that it has a marshalling step where it's going to do. I think you're always going to get a copy on the LabVIEW to Python boundary anyway. So yeah, and this is what bugged me. Like, I've been doing this other project where it's like avoid all copies. I'm looking and saying, well, there's a copy there, there's a copy here, there's a copy there. The problem's got to be to reduce a copy, and it turned out it wasn't quite true, or not an explicit one anyway. Yeah, exactly. Yeah, so Python, the way LabVIEW works with Python, I don't actually know how it talks to it, but it actually even runs a separate executable to contain the Python stuff. Like,
yeah. Sorry, I'd always assume that for the Python node that it must be passing it just via standard in and standard out, or there's some additional LabVIEW Python wrapper that is actually being called and then calling your Python function. And there's a bit of
I don't know. I reckon. I doubt it's written for very high efficiency, though. Let's put it that way.
Yeah.
Or it's probably written for reasonable efficiency, but I mean, the most efficient you can imagine is it's flattening the data and sending it over some kind of pipe, like so standard in, standard out, or TCP based, or something like that. So it must drive from that. DLLs, I mean, would be a much more efficient way to achieve this stuff. But I mean, I don't know. Is there still an OpenCVC API? I know VB was working on trying to wrap some of it directly.
I think I've just gone C++, and then that just compiles. You still have to use.
You wrote something to wrap it yourself.
Yeah. I'm doing so much in C++. It's like that, and then also if you're using, you can use the LabVIEW memory function. So then you can use essentially from C++ allocate memory that LabVIEW can then manage, which makes life a lot easier than trying to pass raw C pointers back to LabVIEW and then try and convert those into a meaningful thing. And
so
then
you went that way,
yeah. So it's much more like C++ than I'd want to when I like doing LabVIEW, but it's kind of where I got stuck. But it does mean that I have I'll be able to share some code soon, but that means I can sort of read IMAC and PixMap messages of different like image formats and then sort of put those into a OpenCV mat formats and then play with those. That was a lot of scoring or looking at block diagrams to see how they're compressing, or whatever, trying to store image data in various forms of unsigned 8-bit integers. But yeah, so I mean, maybe we can create a forum group or something that talks about LabVIEW image formats. Because I think Dataflow also has some DLL based image manipulation stuff, but I think that's using essentially just like basic array, just essentially buffers of images and then various libraries that can read and write those and do other stuff. There's some interesting stuff.
The external DVR, though, I do like the sound of. I think in this case that would. I've been trying to get my head around. I've got another project where I'd really like to, but like you say, start using the external DVRs in C or C++ as well, and then it gets a little over my head, to tell the truth.
Yeah, they're not that well documented.
Or not over my head, I just haven't. Yeah, like you say, they're not documented. I was like, I found a couple of threads on LabVIEW that's like, you kind of need to call this call and this call, and I'm like, I don't. Okay, I'll find an easier way for now.
I have that. I do have some codes to read an eDVR into OpenCV, but I'm not sure I'm using it correctly. The only example I found publicly was from that LavaG thing in the CUDA, OpenCUDA, or whatever it is, not OpenCUDA, the LabVIEW CUDA toolkit, where they sort of they give you a little bit of the behind the scenes on an eDVR, and it's enough to then work out what's going on with an image, but you still have to maybe manage the context, which is like your application instance. And one of those calls always fails, but I don't really need the context, so I don't mind. But it'd be nice to know why it is failing. And then there's things like, LabVIEW is typically sort of when it stops or when the creator of a DVR finishes that, it clears up that DVR, and then it's like, what's happening in the background? Am I making sure that I'm cleaning up my resources afterwards? So there's still a bit more exploration there, I think. I don't know if
that's cool. I'd like to understand some of that, because like I say, I mean, I'm expecting to go to Rust a lot more for any kind of processing stuff, and generally hopefully it'll be a bit more side by side, or when I have done it, to be honest, I just passed pointers around. Let's see, handle all the memory. In that case, we had to do a bunch of we had to do a block allocator anyway, so we just wanted C to manage all the memory, and we just sent pointers around the place. But I can see in other cases, especially if you wanted to wrap anything up reusable, you probably need to start figuring some of that stuff out.
Yeah, and the only other thing that I found is like the iMac, what is it? iMac MX, the camera, the sort of more modern camera driver.
Oh yes, yeah.
Really struggles over your sort of standard HD image. I think it's the limitation of on Windows, you whatever it is, Direct Draw or something like
Direct. Yeah, it uses
yeah.
one of those under the hood for USB anyway. Yeah.
So yeah, that for me, for one of my applications, it's like you really feel the latency pop up above that, and that's frustrating when you're trying to have like live camera feeds. And you can use them well from the C++ side. I can write stuff that uses the more modern Windows Media Foundation stuff, but that's also like really poorly documented and quite complicated. And so yeah, at some point I'll hopefully get something that makes sense and can share it with people, and they can take it from there or whatever. But yeah, it's fun to see what other people are doing with it. Right, I'll stop.
That's right. I was going to say there's a question for you actually. Oh. The thing you're asking, any good resources of mixing C++ and LabVIEW? Like, so you said you found some LavaG stuff.
Yeah, I do have. If you selfless self-promotion. I did a talk at last year's which one's this one? GLA, on calling code from another dimension. That's like C++ and LabVIEW DLL type stuff. That had some good hints and tips.
It's going to look organized. Perfect. I'm gonna have to go look at that as well then.
Yeah, I'll just give me a second. I'll pull up the link. I think it's on my GitLab. Yeah. What have I got? Talks. Sorry, this is
right. I'm gonna answer. I can see your question, Imran, as well about Linux RT priorities. So I think I have a quick answer to this, which is for timed loops and things like that. What you put in ends up being the Linux thread priority, I believe, because it's inverted compared to everything else. Thank you, John. I have to look at that as well. And there's YouTube. Perfect.
Yeah, great. Oh, yeah, someone's found it.
I go back to that. I can't remember. Yeah, maybe I missed that last time. That looks cool. Yeah, because I'm going to be doing a lot more of that. Yeah, LabVIEW manager functions are the bit that I need to kind of get my head around, which I'm starting to. It's one of those things, there's a lot of legacy stuff in there, right, as far as I understand. There's like one whole set of APIs that but you don't use that anymore, you use this one.
Yeah, the resources refer to the C integration node and other such things. So it's like a bit of LabVIEW archaeology and the Lava forums where the real sort of those who have been in the trenches lurk and can provide very helpful insight. And then the other one there's a NI released their gRPC library, and if you're interested in doing like building for multiple platforms without having to have LabVIEW installed on all those different platforms, then that has an example of dynamically loading in the LabVIEW exported memory manager functions. So the LabVIEW executable provides externally linkable functions, which you can then dynamically load into your C++ whatever code. And that means that when you're building, you don't need a copy of Xcode.h and other LabVIEW type around, because you're just loading them dynamically. So I've been playing with that, and that's quite fun. But I sort of had to crib from some NI employee mentioned it on the gRPC DLLs. There's all sorts of they're slowly sort of hinting at what might happen under the hood, which I mean, thing is, if it's not officially supported, you don't necessarily
that's it.
Pin your whole project on it, but there's some fun stuff to be done.
The gRPC thing is something I want to play with again. Last time I tried the NI library, I was a bit. It looks like it's improved a little bit. I'm not entirely convinced by some of the design decisions, but we'll see. I don't trust anything that auto-generates LabVIEW code. That's my problem. And it's all like intertwined with your own code. I'm like, I'm going to lose some software here. But I guess Git will save that if it ever happens.
I've not played with it yet, but it's on my list of things to dive into, much like Rust. Although I fear if you're integrating LabVIEW and Rust, lots of it's in this sort of unsafe Rust area where, Yeah,
I mean, it's not too dreadful because, I mean, you just, the final layer, if you're building Rust to a DLL, is technically unsafe. But you know, that's the way I've always done it anyway. Is you just build it out to DLL, so it just looks like a CDLL to LabVIEW really. I have played with the gRPC library to that as well, which is the other way to do it. Because, Rust has good gRPC support, so I need to play with that a little bit more. I'll return the favor. I'll tell you what, I have it's not particularly sophisticated, but I have a GitHub where I did just an example of a Rust project that was built and called from LabVIEW.
Yeah, that sounds fun. I'll have to take
a look. It does look a little bit. Yeah, you do have to do a little bit with the Rust to make sure it cleans up the memory as well, like you say, because normally Rust will just they call it drop, automatically clean up after itself. But you have to tell it, no, I've sent this to LabVIEW, so don't kill the memory until I tell you it's safe to. So there's a little bit of unsafe stuff in, but not too bad.
I guess that's it. You're trying to minimize your exposure where, you know, other buffer overflows or other memory management you don't want to care about. You just want to trust that it's safe and well managed.
That's it. Yeah. So that's kind of, I've been wrapping some of the NI APIs as well for like GACMX and stuff in Rust, and that's the same thing. Yeah, at some point it's unsafe because you're talking to C, but you just try and put a good layer on top. That's pretty easy. You're gonna make your actor manual. Yeah, I don't use the actor framework. That's so I can't quite comment on that. Yeah, so I don't use the code generation there either. But that one seemed a bit more like you do it once and that's that though. I think that's the problem. The gRPC stuff, it creates like a library and then you put your own code in that library. And so if you regenerate it, it's the mixing of the two. Like I think there would probably have been a way to do it, and I think there's even a comment on this on their GitHub that this would be nicer. Is have like an auto-generated interface that you then write your custom LabVIEW code to. So the auto-generation reruns here, changes the interface, then it still breaks, but you've kind of got a bit more control over where that break happens, and it's not going to stomp on anything that you've done in the code. It may be an unfounded concern, but I just, as soon as I saw that, I thought, I don't trust. Yeah, I mean, when you're doing scripting with all the context issues and stuff like that, just always wait for something to break. But I'm probably being overly cautious. Yes,
right.
we'll see that as well. Yeah.
I'll let you get back to answering other questions, but thanks for the chat. And
no, thank you. Yeah. No, it's really interesting. I look forward to looking at what you've got.